So, very good afternoon to all of you. Before we begin, does anyone has any doubts that they would like to ask? No. Okay. So let us begin with the problems. So let's solve first problem. Okay. So the question reads: compute de Broglie wavelength of electron with kinetic energy 25 eV, and your options are 5.02 angstroms, 2.45 angstroms, 1.33 angstroms, 0.56 angstroms. Okay, so a very basic question. So what we have to do, we have to calculate de Broglie wavelength, and we are given that the kinetic energy of electron is 25 eV. Okay, so how do we solve this one? Okay, so let's say we are writing de Broglie wavelength as lambda, and we know that this lambda is nothing but h over p, where this is your Planck's constant and p is momentum, right? But what we are given is kinetic energy, and what is the relation between kinetic energy and momentum? So we can write kinetic energy as half mv squared, right? Or we can multiply by m in both numerator and denominator. So what we will get is 1 upon 2m m squared v squared, right? Okay, and now what is mv? Mv is momentum, so this becomes p squared, so this just becomes p squared over 2m. Therefore we can write p as 2m times ke under root. Oops. Okay. Okay, so then this is the kinetic energy. So then our lambda will become h upon under root 2m multiplied by kinetic energy. Now we know the values. So our h is 6.626 times 10 to the power minus 34, right? And then this root becomes 2 times mass of electron is 9.11, 10 to the minus 31 kgs, and the kinetic energy is given in electron volts, right? It is 25 eV. So what we will do is we will convert it to joule. And how do we convert that? We multiply it by the charge of electron, 1.6 times 10 to the minus 19. Okay, and root over the entire thing. Okay, and then if you solve this, what you will get is 2.45 into 10 to the power minus 10 meters, which implies your lambda is 2.45 angstroms. So this is your correct answer. Now, as you can see, there are a lot of universal constants in this thing. So what we can do is, in this formula, we can even generalize this thing, and we can write lambda as h over under root 2 times mass of electrons times the charge of electron and times the potential in which it is being accelerated, right? So this is now your kinetic energy, EV, right? If you apply potential V and accelerate it in that potential, so the kinetic energy of the electron is EV. So what you can do is you can substitute the values of H, 2m and E, and then what you will get is you can write lambda as 12.27 angstroms divided by root V. Okay. So for example, in this case, V was 25. So your lambda will be 12.27 divided by under root 25, which is simply 5. And this will give you 2.45 angstroms. Okay. So if you want to remember this value, this will make your life easier, much simpler. You just have to plug in the value of the voltage in which it is being accelerated, and you can directly get the value of t Broglie wavelength. Or you can solve it conventionally, just like how we did earlier. Okay. Any doubts in this one? Okay. Then let us solve the next one. So what is the next one? We have a positronium. Okay, we have a positronium atom. Now what is a positronium atom? So a positronium atom has plus electron instead of nucleus and a minus electron revolving in the orbits. So it is like hydrogen atom, but instead of your proton, now you have a positron at the center. So this is positron. Okay. So this is your positronium atom. Okay. So a positronium atom consists of a positron and an electron. Calculate the reduced mass of positronium atom. Okay. So the options are So I'll explain the question once again. We have a positronium atom, and this is the positronium atom which we have drawn here. Now at the center we have a positron instead of positron instead of proton. Okay, and then we have an electron outside. And what we have to do is we have to calculate the reduced mass of this atom. Fine. Now, how do you define reduced mass of any two-body system? Anyone? So if you have two objects of mass m1 and m2, okay, what will be the reduced mass mu? I think this was taught in the class. Anyone? Okay. So mu is defined as m1 m2 over m1 plus m2. Okay, and this comes from this equation. So this is the definition of reduced mass: 1 over mu 1 over m1 plus 1 over m2. Okay, now here we have a positron. Okay, so positron is like an electron, so both have same mass. Okay, so let me write. So you have positron, you have electron. Mass is same in both the cases, which is me. This is how much? This is 9.1 into 10 to the minus 31 kg. And this has a charge of plus E, and this has a charge of minus E. Okay? So because both have same mass, me, so in this formula, we can just, instead of m1 and m2, we can write me. So what we will get is, we will get me squared over 2me, right? And this will be nothing but me over 2. And me we know is 9.1 into 10 to the minus 31 kg, and dividing it by 2 will roughly give us 4.5 10 to the power minus 31 kg, right? So the correct option will be option A. Any doubts in this one? Yeah. Okay. So let's move on to the next one. Also, if you do not understand anything at any point, please feel free to stop me, open your mic, unmute, or even if you are hesitant, you can type your questions in the chat box. I'll read the chat. Okay, but please don't be hesitant. Okay, so let's solve next question. So the next question is, in the previous problem that we just solved, what will be the value of Rydberg constant if RH, where H is hydrogen atom, if RH is given to be 1.0 974 into 10 to the 7 per meter. And your options are 1.0974 into 10 to the power 7 meters, which is exactly the same as RH, or 5.487 into 10 to the power 6 per meter, 1.0974 into 10 to the power 6 per meter, or 1.974 into 10 to the power 7 per meter. Okay, so in the previous problem we had a positronium. Now let us redraw the positronium. So here we have plus E and outside we have minus E. However, for hydrogen we have a very heavy mass here and we have a proton here, right? We have a proton here and we have an electron here. Okay, so for hydrogen we are given that RH is 1.0974 into 10 to the power 7 per meter. Okay, and now we are asked to calculate the Rydberg constant for a positronium. Now if you remember, what is the equation for Rydberg constant? So your Rydberg constant R, that is given as mu times e to the 4 over 8 epsilon naught squared C h cube, right? And when this mu is me, so what we will get? RH. Okay, so we can write our Rydberg constant as mu times RH divided by me. Okay, so in this equation you can see when mu and me are equal, then you will get R as RH, right? So this is consistent with our assumption. Okay, now in the previous problem, what value did we get for mu? So mu for positronium, mu p, that was me by 2, correct? That was half the mass of electron. So plugging it in, we get R as me times RH over 2 me. So this me cancels out and we get RH over 2. And RH is already given to us here in the problem. So this will then become 5.487 into 10 to the power 6 per meter, which is option B. Okay. Any doubts in this one? No? Okay. Just give me a second. Let's solve next one then. So, sorry. So the next one is compute de Broglie wavelength of a ball of mass 5 grams and speed 2 meters per second. So we have options like 2.58, 6.626. Okay, all these are in angstroms. 4.02, 3.32 power minus 32 angstrom. So we did a very similar question in the beginning, and we know that the de Broglie wavelength will be simply h over p, right? And what is p here? So p is nothing but mass times velocity, so h over mv, correct? And now what is mass? So mass is 5 grams. Converting it to SI units, this becomes 5 into 10 to the minus 3 kg, and V is 2 meters per second, which is already in SI units. Okay, so then our lambda becomes 6.626 into 10 to the power minus 34 divided by 5 into 10 to the minus 3 multiplied by 2. Okay, so this becomes 10. 5 times 2 is 10, and multiply by this, so this will become 6.626 into 10 to the power minus 34 over 10 to the power minus 2. Okay, these values will be in meters. Okay, therefore here lambda becomes 6.626 into 10 to the power minus 32 meter, which is option B. Okay, because so before solving the next problem, let us solve one uh, non-numerical type problem just to check our understanding. Okay, so the question reads, what is the drawback of Moore's model, right? And you have four options. So first is valid only for single electron atoms or ions like hydrogen, helium plus, lithium plus plus, etc. Okay. B is can't explain fine structure. C is can't explain splitting of spectra or splitting of spectral lines in presence of electric or magnetic fields. And your option D is all of the above. Okay. So there is nothing to solve in this, right? This is standard information. If you have watched the lectures for week 3, you will be easily able to give the correct answer. So does anyone know the correct answer? Hmm? You can type in the chat box if you are uncomfortable unmuting your mic. D. Yes, thank you for the answer. Otherwise, the session was becoming very non-interactive. Okay, D. So all these things are correct. That the Bohr's model is valid only for single electron atoms. It cannot explain fine structure, and it cannot explain splitting of lines in presence of electric and magnetic fields. So this phenomena is called Stark effect and Zeeman effect, respectively. So when the when the spectral lines split in presence of an electric field, that is called Stark effect because it was discovered by Stark. And when they are splitted in presence of magnetic field, that is known as Zeeman effect. Okay, and Zeeman effect will be discussed in the next week's lecture, I guess. So we'll dive deeper into Zeeman effect next week. Huh. Okay, so let's solve this one. The degree of degeneracy of the nth energy level in hydrogen atom is n squared n over 2 n plus 1 over 2 or under root n. Okay, so if you can solve this one again now, please type your answer in the chat box. Okay, and we can all solve it simultaneously, and let's see if we get to the same answer. First of all, what do we mean by degeneracy? Degeneracy means same energy. Okay, so two levels are degenerate if the energy of both the levels is same. Now, what we are asked to find is that there is some nth energy level of hydrogen atom. Okay, and we are asked degree of degeneracy, which means how many states of same energy are there in the nth level, in the nth energy level. Okay, so this is a rephrasing of the question that we have done. Okay. Now we know that there are different quantum numbers. So one quantum number which is given to us is n. Correct. Now correspondingly we will have L, right? And L will have values 0, 1, 2, so on, all the way up to n minus n. Correct. And similarly, we will also have m, and m will have values from minus L to plus L, right? So for example, if this is your first energy level, okay, so if n is equals to 1, then this is just 1, right? And L is only 0, right? Because it has to go only up to n minus 1, and your m is also 0. So how many states are there in total? One, just one state, right? You have only one possible value of n, one possible value of L, and one possible value of m. Okay, let's see for n is equals to 2. Now you will have the second state, the second energy level. Here you will have two values of L, 0 and 1, right? So when your L is 0, your ML will be 0. But when your L is 1, your ML will have three values, minus 1, 0, and plus 1. So this corresponds to 1s, right? This corresponds to 1s. Let me write here. Okay. So this is 1s. This is your 2s orbital. This is your 2p orbital, right here. This is your 2p, and this is your 2px, 2py, or 2pz, depending on the direction of the field. Correct? So how many states are there for n is equals to 2? So we have, this is 1, and then this is 2, 3, 4. So we have total 4 states. Okay? So when n is 1, our states are 1. When n is 2, we have now 4 states. Okay? Similarly, when your n will be 3, so this will be 3, and this will have values 0, 1, and 2, and again this will have 0, minus 1, 0, 1, and this will have value minus 2, minus 1, 0, 1, 2. Okay, so how many states will be there? So this will be 1 plus 3, 4, and then plus 5, 9. So you will get 9 states. Now you can already see that the degree of degeneracy, these values, they are nothing but n squared, right? So the correct answer will be n squared. Okay, any doubts in this one? Now we can even solve it in a more generalized way, because you may think, okay, this is true for only the first three states, but what about some random state? Okay. So, but to solve it like that, we have to solve one AP series. Okay. Now, just like how we did here. Okay. So notice one thing, that for nth level, we have n minus 1 L values, and for each L, we have 2L plus 1 values. Correct? So for nth level, the total states that we will have will be L goes from 0 to n minus 1 to L plus 1. Okay. So when L is 0, this becomes 1. When L is 2, when L is 1, this becomes 3, then 5, then so on, all the way up to when this becomes n minus 1. So 2 n minus 1 plus 1. Okay. And we can rewrite this term as 2n minus 1. Yeah. Just opening the brackets. So what is this? This is an AP series. AP is arithmetic progression. And now we have to calculate the sum of an AP series. Now, do you remember the formula for sum of AP series? So the sum is given by a by 2 times 2a plus n minus 1 d, where a is the first term, which is 1. So this will become half times 2 plus, and n is the number of terms. So how many terms do we have here? We have n minus 1 terms here, right? We have n terms here. So then this will, and d is 2, which is the difference. So then this will be n minus 1 times 2. This is n over 2. Okay. Now if you open this bracket, so you'll get n over 2, 2 plus 2n minus 2, which is nothing but n over 2 multiplied by 2n, and 2 cancels out, so this becomes n squared, right? And this is the answer that we got here. Okay, any doubts in this one? No? Okay, fine. Okay, let's try a little simpler problem. So the problem is calculate speed of electron in first excited state of hydrogen atom. Your options are 2.2 10 to the power 5, 3.7 10 to the power 5, 10.9 10 to the power 5, and 5.4 10 to the power 5. Okay, so let us write, okay, let us draw hydrogen atom first. So this is your nucleus, and this is your electron, which has mass m, and it is in let's say first excited state. Okay, so we know that the centripetal force mv squared by r, that is given by the electrostatic force 1 over 4 pi epsilon naught e squared over r squared, right? So this r will cancel here, so we get mv squared is equals to, this value is 9 10 to the 9 e squared over r. Okay, or we can write mv squared times r is equals to 9 into 10 to the 9 e squared. Now we also know that angular momentum L, which is mvr, that is quantized, and that is given as nh cut. Correct? So when we divide these two equations 1 and 2, what we will get? So this mvr will cancel out, and we will get r equals, yes, no sorry, we will be left with v. So v equals 9 into 10 to the 9 e squared over n h cut, right? And because it is in first excited state, what will be the value of n? N will be 2, right? So n is equals to 1 is the ground state, and n is equals to 2 is your first excited state. So we can put n is equals to 2 here, and we will get v as 9 into 10 to the 9 upon 2 h cut e squared. Now we know value of e, so e is nothing but 1.6 into 10 to the power minus 19, and h cut is nothing but h over 2 pi, and we know h is 6.66, sorry, 6.626 into 10 to the minus 34. So we can then plug in both the values of e and h cut in this equation. And what we will get is, we will get v as 10.9 into 10 to the power 5 meters per second. Okay, which will be option C. Any doubts in this one? Or if you already know what is the velocity of ground state, so what will be the velocity of ground state? That is 2.18 to 10 to the 6 meters per second. Then you can write velocity of any nth state, that will just go as velocity of ground state for n. That's it. So here you can just plug in n is equals to 2, and you will get the same answer. Okay. So let's do one more, and again, please type your answers in the chat box for this one. This again is a non-numerical type problem. If you have watched the lectures, then you will be able to answer this. Okay. In Sommerfeld's model, so we have Sommerfeld's model. If k is your azimuthal quantum number and r is the radial quantum number, and r is the radial quantum number, and n is your total quantum number, then k into nr is equals to n. Option B. K divided by nr is equals to n. Option C. K plus nr is equals to n. Or option D. K minus nr is equals to n. Okay, which is the correct answer? A. No, it's not A. Okay. So n is your total quantum number, right? So what is there in Sommerfeld's model? So we know that Bohr considered a circular orbit, right? So this was Bohr, but Sommerfeld considered one elliptical orbit, correct? He considered one elliptical orbit, and he said atom is at one of the focus of the ellipse, right? So what happens here? Your r, which is radius of your orbit, that is constant, right? That is constant. Only your theta, that is changing, right? So here your r is constant and theta is changing. Therefore, you get only one quantum number, which is n, and this corresponds to your angular momentum. Correct? So, because we know that L is given as n h cut. Okay? But in Sommerfeld's model, if your electron is here, then its distance from the nucleus r, that is also changing, right? For example, when it goes here, now your r has changed, it has become some r prime. So here r is not a constant, here r is also changing, and of course your theta is changing, right? So because your r is now changing, so you'll get one additional quantum number, which is nr, right? As we are given here, nr. This is the radial quantum number, and because your theta is changing, so you will get one quantum number k. Okay? Now we have two quantum numbers. Earlier we only had one n. Now we have two. We have nr and we have k. So the total quantum number n is defined as nr plus k. This is the total quantum number. So correct option is C. So the next problem is the wavelength of H alpha line is 6563 angstroms. Calculate the wavelength of same line for tritium 1H3. Okay. So instead of hydrogen, now we have to calculate the same wavelength for another atom, which is known as tritium. So what is tritium? Let us draw hydrogen. So it has one proton, right? It has one proton and one electron. But for tritium, it will have one proton but two neutrons and one electron. Therefore, its atomic mass will be 3. You can see we are given mass as 3, and this is your charge. So charge is 1. So therefore, we have one proton, two neutron, and you can see that this is the charge is balanced, right? Proton has one positive charge, electron has one negative charge. So the resultant charge is 0 because neutrons does not have any charge. Okay, so we are given that the wavelength for H alpha is 6563 angstroms for hydrogen, right? And we have to calculate the wavelength for same line for tritium. Now, what is this H alpha? So H alpha is the red color spectral line that we see when we have the first transition in Balmer series. So what is the first transition in Balmer series? So this is your N is 1, N is 2, N is 3. So Balmer series is, so the first transition in Balmer series is this one, from 3 to 2. This is your Balmer series. So the spectra that we get, that is known as H alpha spectral line. Okay. So what are our options? Our options are 6560.6 angstroms, 6563 angstroms, 6572 angstroms, 6620.5 angstroms. So let's first write for hydrogen. So for hydrogen, we have 1 over lambda h given by RH over 1 over 2 squared minus 1 over 3 squared. Okay, because the transition is from n is equals to 3 to n is equals to 2. So this is simply RH times 1 over 4 minus 1 over 9, which is just 5 by 36 RH. Okay. Similarly, we can write for tritium 1 over lambda t. This will be some new Rydberg's constant for tritium and same transition, right? because this is safe. So this will be 5 over 36 RT. Okay. Now we know that this Rydberg atom has effective mass, right? So the Rydberg constant is proportional to our effective mass mu, and then for any atom we can write Rm. Okay, that is just R infinity upon 1 plus m by n. Okay. So for hydrogen, this will become RH is equals to R infinity upon 1 plus mass of electron over mass of hydrogen atom. So the hydrogen nucleus. Okay, and for tritium, RT will become R infinity upon 1 plus m by mass of tritium. Correct? So now we have these two equations, 1 and 2. Let us divide 1 over 2. So what we will get is we'll get lambda t over lambda h, and 5 over 36 will cancel out. This will be nothing but RH over RT. And then we can plug in the value of RH and RT from here. So R infinity will cancel out and we will get 1 plus m over mass of tritium divided by 1 plus m over mass of hydrogen. Okay. Now mass of tritium, this is 3 times mass of hydrogen, right? Because it has 1 proton and 2 neutrons, right? So we can write it as 1 plus m over 3 mh divided by 1 plus m over mh. Okay. And now we know the ratio of the mass of electron and mass of proton, m over mh, that is 1 over 1836, right? So a proton is 1836 times heavier than electron, and when we plug this value in, so we get lambda t over lambda h as 1 plus 1 over 3 times 1836 divided by 1 plus 1 over 1836. Okay. So upon solving further, we get lambda t is lambda h times, so this will be 3 into 1836 plus 1 over 3 into 1836 plus 1. Okay, so this will be 3 into 1836 plus 1 divided by 3 into 1836 plus 3 times lambda h. Okay, so lambda t will be 5408 plus 1, 5408 plus 3 times lambda h, or 5409 upon 5411 times lambda h. And if you and lambda h is given to us as 6563 angstroms. So if we solve this, we get 6560.6 angstroms. Okay. So which is option A. Yeah. Let's solve 10th question, which is calculate the ground state energy of positronium. Okay. If for hydrogen ground state energy is minus 13.6 eV, okay. So we know that energy of electron in nth state, so that is written as En, is mu times e to the 4 over 8 epsilon naught squared h squared multiplied by 1 over n squared. Okay. Now here mu is the reduced mass. Okay. Mu is the reduced mass. So for H atom, mu is just the mass of a proton, right? Mu is mass of proton times mass of electron upon mass of proton plus mass of electron. Okay, because this mass of proton is very large compared to mass of electron, we can assume that this is mass of proton times mass of electron divided by mass of proton, and then this cancels out. So for hydrogen atom, we get mu is roughly mass of electron. And we had already calculated for positronium. So for positronium, we solved earlier that mu is mass of electron divided by 2. Okay. So for positronium, En will be mu by 2. En will be Me by 2 e to the 4 upon 8 epsilon naught squared h squared 1 over n squared, and this is simply whatever we get for hydrogen, so E of hydrogen over 2. Okay. And for hydrogen this is minus 13.6 eV, so we get for positronium this will be minus 6.8 eV, which is option C. Any doubts? Okay. So the next problem, calculate energy required to remove electron from first excited state of lithium plus plus. Okay. Options are 13.6 eV, 30.6 eV, 122.4 eV, or 3.4 eV. Okay. So what is the atomic number for lithium? This is Z equals to 3, right? And what is the ground state energy of hydrogen? So that is 13.6 eV, right? So then we know that any energy that is proportional to 13.6 z squared over n squared. And because it is first excited state, your n will be 2 and your z will be 3. So this will be 13.6 multiplied by 9 divided by 4. Okay, so this will be 13.6 multiplied by 2.25. So your En comes out to be 30.6 eV, which is option B. Okay. According to Bohr's theory, angular momentum of fifth order orbit is, and you have four options: 25 h over pi, 1 h over pi, 10 h over pi, or 2.5 h over pi. So for fifth order orbit, where n is 5, and we know that angular momentum L is conserved, sorry, it's quantized as n times h cut. So for fifth order orbit, this will be 5 h cut, and h cut is nothing but h over 2 pi. Okay, so we get L as 2.5 h over pi. So D is the correct answer. Hmm. So let's do the 12th problem. Okay, so the problem is that we have Bohr series of lines, which is the hydrogen atom spectra, and the third line from the red end, that will correspond to which one of the following interorbit jumps of electron for Bohr orbits in an atom of hydrogen. Okay, so we have different levels, and we have n is equals to 1, 2, 3, 4, 5, and so on. Okay, so this is n is equals to 1, 2, 3, 4, 5. So what is this red end? So red end, this is the H alpha line, and this corresponds to the transition from 3 to 2. So this is the first line in the Balmer series, which is the visible uh, region of the hydrogen spectrum. Okay. So this is your first transition, right? This is your first transition, 3 is to 2, and it gives you the red line. Okay. So this is the first one. What will be the second one? The second one will be this one. This is your second one. And then what will be our third one? The third one is this one. So this is our answer. This is the one which we need. So this is the one. So what is the transition? The transition is from 5 to 2. So the correct answer is A. Okay. So we have one electron in 4f orbital, and what we are asked is which of the following sets of quantum numbers is correct. Okay. So first set is n is 4, L is 3, your M is 4, and your S is half. Your second option, N is 3, L is 2, M is -2, and S is half. Third option, N is 4, L is 3, M is 1, and S is half. Fourth option, N is 4, L is 4, M is -4, and your S is -half. Okay. So what is the meaning of 4f orbital? So 4f means n will be 4 because it is written here, right? And what are the orbitals? S, P, D, F. So this corresponds to n is equals to 0, 1, 2, 3. So 4f means n is 4 and L is 3. So how many options can we see that have these two answers? So one is here, we have n is 4, L is 3, and the other is here, n is 4, L is 3. So we can simply rule out option 2 and option 4. Okay. Now we also know that our m goes from -L all the way to +L. Okay. Because L is 3 here, so our m can be anything from -3, -2, -1, 0, 1, 2, 3. Option 1 says m is 4, and this is not possible, right? So we can rule out this option. M is equals to 1, this is possible, you can see here. So option 3 is the correct answer. So this problem is about transition. Okay, so there is an electron in hydrogen atom. This undergoes a transition from an orbit with quantum numbers ni to another with nf. So vi and vf are initial and final potential energies. If vi over vf is 6.25, then smallest possible nf will be, and options are 3, 4, 5, 6. So how do you define potential energy in the Bohr's model? So we define potential energy V as minus 1 over 4 pi epsilon naught Z E squared over R, right? And we know that for Bohr's atom, R goes as 0.529 n squared over Z. Okay. So what this implies is that V is proportional to 1 over n squared. Okay. Now what we can then write is, we can write Vi over Vf, we can write it as Nf squared over Ni squared, and this is given us to be 6.25. So if we take the square root on both sides, we will get Nf over Ni is equals to under root 6.25, which is simply 2.5. Okay, so your Nf is 2.5 times Ni. And because these n's are integers and the value starts from 1, so when Ni is 1, your Nf is 2.5, but this is not an integer, right? This is not an integer, so we must put Ni is equals to 2, and then we get Nf as 5. Now this is an integer, and if we keep on increasing the value of Ni, we'll get higher values of Nf, but what we are asked is smallest possible Nf, so that will be 5, option C. Okay. So next problem. Consider H atom with electron in nth orbital. Okay. Now you have EM radiation of lambda is equals to 90 nanometers is used to ionize the atom. If kinetic energy of ejected electron is 10.4 eV, then the value of n is, options are 1, 2, 3, 4. Okay, and it is given that Hc is equals to 1242 eV nanometers. Alright, so let us start solving. So first of all, we are given wavelength of the incident X-rays. Okay, so this is the electromagnetic radiation. The wavelength is 90 nanometers. So we can calculate the energy of incident photon, and we know that energy of photon, that is nothing but h nu or hc by lambda, right? We are given the value of hc here, 1242 eV nanometers, and lambda is also given us to be 90 nanometers. Okay, now the energy of electron in the nth orbital, that is given as En, and you know that this will be 13.6 divided by n squared. Okay, so this is the ionization energy. And finally, the kinetic energy of the electron, that will be the energy of the photon that we had, and then it transferred all of the energy to the electron, but some of the energy was used in ionizing the electron. This will be Ep minus En. Now we can write this as 1242 over 90 minus 13.6 over n squared. And what is the kinetic energy that is given to us? That is given to be 10.4 eV. Okay, so we get this equation. And now what we have to do is we have to calculate n. So first let us put this one here. So if you divide by 9, this will be 10, and if you divide by 9, this will be 1, 3, 8. Okay, so this becomes 13.8. So we have 13.6 over n squared, that is nothing but 13.8 minus 10.4, and if you subtract you will get 3.4. Okay, so n squared is then 13.6 divided by 3.4. Okay, and then this becomes, so this is roughly 4, and this implies n becomes 2. So it was in your second orbital to begin with. So this was question 15. Next will be 16. So we have n is equals to 3. Okay. So when you have n is equals to 3, your L can be 0, 1 or 2. Okay, so this will be S, P, D. So how will our orbitals look? So we can actually draw the orbitals. So this will be your S orbital. This will be your P orbital, and it will have 3 values of ms, right? So here your L is 0 and your ms is also 0. Here your L is 1 and your ms is -1, 0, +1. And next we will have d orbital. Here your L will be 1, so your ms will, your L will be 2, your ms will be -2, -1, 0, +1 and +2. Okay. Now we are asked the maximum number of electrons that can have the principal quantum number n is equals to 3 and spin quantum number ms has -r. Now if we fill these, we can actually fill these, and both will have 2 electrons, up spin and down spin. And because we want the maximum number, we will fill them all up. Right? We will fill them all up. And if you now count the down spin electrons, which corresponds to -half spin, so here you'll have 1, here you'll have 3, and you'll have 5. So if you add them up, you'll get 9. So the correct answer is 9. Okay. So alternatively, we solved previously one problem where we found out that for any nth orbit, there are n squared states, right? There are n squared degenerate states, and each state can have 2 electrons. So there will be 2 n squared electrons, correct? And now half of these electrons will be upspin and half of these electrons will be downspin. So n squared will have plus half spin and another n squared will have minus half spin. Okay, so for any nth orbit there will be n squared electrons with downspin. Okay, so here we were given n as 3, so n squared will be 9. Okay, so this is another way to solve this problem. So next question is about muon, and it comes from cosmic rays and is trapped by a proton. To form hydrogen-like atom. Okay, so muon is 200 times heavier than electron. Okay, now the question is, what will be the longest wavelength? Of the spectral line in the analog of Lyman series of such an atom. Okay. And these are different options. So 5.6 angstrom, 6.67, 3.75 or 13.3 angstroms. So first of all, let us draw hydrogen atom. Here we have one proton and here we have one electron. Now for this muon-like atom, here we will have one proton, but here we will have one muon instead of an electron, and its mass is 200 times the mass of electron. Okay, so if we calculate its reduced mass, so here mu will be mass of proton times mass of muon upon mass of proton times plus mass of muon. Okay, and now let us replace the masses. So we solved one problem earlier where we used that proton is 1836 times heavier. Okay. So our mu will become, this will be 1836 times mass of electron multiplied by 200 times mass of electron and upon the same thing but addition. So this Me will cancel out one of the Me and we'll be left with 1836 into 200 divided by 2036 times Me, and this comes out to be, so your mu is 180 Me. So this is now our reduced mass. For the atom which has muon instead of electron. Okay. Now we know that the energy depends on this effective mass. So the energy in the nth orbital, that will now be mu over me times minus 13.6 over n squared, right? So this is then nothing but 180 into minus 13.6 over n squared. Okay, where this minus 13.6, this is, let's say, the ground state energy Eg. So you can write En as 180 Eg over n squared for this muon like atom. Okay, so for the ground state, E1 will be 180 Eg, right? For first excited state, E2 will be 180 over 4 Eg, which is nothing but 45 Eg. Now we are expected to calculate the longest wavelength of the spectral line in the analog of the Lyman series. So the Lyman series is, let's say you have all the levels like this, and the Lyman series forms when you have transitions like this. Okay, so the longest one, the wavelength will be longest when the energy is minimum. So this one corresponds to our longest wavelength, which is from 2 to 1, the transition from 2 to 1. Now we already have the energies of 2 and 1. So delta E, which is E2 minus E1, this will be, E1 minus E2, this will be, E2 minus E1, and this will be 180 minus 45 times Eg, or this is minus 135 Eg. Okay, now we have Eg as minus 13.6, so our delta E will be minus 135 into minus 13.6 EV. So this then becomes 1836 EV. Okay. Now we want to find the wavelength. If this is the energy that the photon will have when the transition happens, so the wavelength will be hc by lambda is delta E, or we can simply write lambda as hc over delta E. Now the value of hc, we just used it in one of the problems. It is 1242 eV nanometers. Okay, so we'll again use the same value. So we'll write 1242 and delta E is 1836, and the answer will be in nanometers. Okay. So if we solve this, we will get lambda as 0.667 nanometers, or we can write it in angstroms as 6.67 angstroms, which matches with option B. So this was the last problem. How many? 17 problems we solved today. Do you have question in any of the problems that we solved? If not, then we can end this class and I'll see you next Saturday, same time. Okay. Again, as usual, I'll write down my email ID here. Thank you for joining. So this is my email ID. If you have any doubts, if you want to discuss anything, if you want
Sir,
to have a,
can you spell it, sir?
so it is MANAVBENIWAL. I will type it in the chat box.
Thank you, sir.
Okay, I have put it in the chat box. If you have any doubts, you want any discussion regarding anything, maybe PhD, career, whatever, we can have a discussion. I'll I can even set up a meeting and we can discuss. Anyway, in any case, I'll be happy to reply to the emails eh, if it benefits you. Feel free to email me. Okay. So, yeah, thank you for joining. Okay. I guess then we can end this meeting.